Hello, hello. I don't think we need the microphone, but it's good. So, hello everyone, and welcome to this talk. We have the pleasure to host Dr. Abdul Rahman Hammoud for a talk on artificial intelligence for downscaling. Dr. Abdul Rahman just graduated with a PhD from KAUST in April 2024, and he completed his master's also at KAUST, and before that, his BE at AUB in mechanical engineering, and I worked with Professor Issam Lais, and done a lot of work on uncertainty quantification and data assimilation, especially in applications related to ocean modeling and pollution risk, things like that. And I think this work is significant, especially nowadays that everyone is using artificial intelligence, and it's still not clear how we can combine our physical knowledge, the physical laws that we know, the constraints that we know of, conservation laws, etc., with these modern AI tools. And I think I'm very excited to see how these tools are being combined with chaotic, especially in chaotic systems and uncertain systems. So very excited about the talk. Take it away.
Thank you. Thank you everyone for coming to the talk. Today I'll be discussing artificial intelligence for downscaling and with application to uncertain chaotic systems. And first we have to thank my advisors, Professors Omar and Rahman at KAUST, my co-advisor Idris Titi from Cambridge, and Professor Olivier Lemaitre, who all helped in making this work happen. And to start with introducing downscaling, we have to understand that downscaling is one of two components of regional state estimation, in which regional state estimation tries to combine in an optimal approach based on some optimality criteria between the data and our models in order to estimate the state of a system, of a dynamical system. And there are two main approaches in regional state estimation, which are downscaling and data assimilation. And in this talk, I'll be focusing mostly on downscaling, in which we're trying to estimate the state of a dynamical system at a high resolution using low resolution coarse scale data. The difference between the two is that downscaling aims to provide a high resolution solution trajectory of a dynamical system, whereas data assimilation aims to improve our forecasts or our forecast skill into the future. Downscaling is the most common approach to obtain high-resolution environmental fields using low-resolution core-scale data. And here, core-scale could be core-scale in time or in space, or both. And the idea here is to build a mapping between the low-resolution data with the high-resolution solution trajectory. And there are two main approaches, and this is how we categorize downscaling approaches, either dynamical through a dynamical model in which we inject core-scale data into the dynamical model to give us a better estimate of the state. The other approach would be statistical downscaling, in which we use a statistical mapping that lifts the core scale data into a higher resolution manifold, a solution manifold, where our state is represented at a higher resolution. And the main challenges in state estimation is model complexities and uncertainties. We will be focusing in this talk mostly on uncertainties, which is the domain that I'm interested in, primarily the uncertainty quantification, in which uncertainties can come from the data side or the model side. Uncertainties in the data can come from the data acquisition, the approach to the sensors, instrumentation, basically. And uncertainties can also come from the model, in which we don't have perfect models. We always have some parameterization, especially in environmental flows, because you can't resolve the entire energy spectrum. You need some subgrid scale parameterization. And here we resort to artificial intelligence as a potential solution in which we look at AI tools for new perspectives to solving these inverse problems or data assimilation or downscaling problems. And here I'm showing two animations of AI for generating advertisements for Star Wars or to play Go at better than human level performance. To start this talk, I'll talk about continuous and discrete data assimilation with noisy observations. And here we want to establish a baseline for downscaling. And the reason why we use downscaling is that Generally, we're interested in chaotic systems in which small perturbations are going to drift our solution away from the reference solution or the solution that's followed by what we observe in terms of data. So basically, these systems are deterministic by their nature, but because our approximations are influencing the solution that we're obtaining, we will never get the exact solution into the future. We're always getting a slightly different solution, and predictability is lost quickly in time. And basically, the solution that is commonly resorted to solve or to get a better representation for these systems is an ensemble-based or a stochastic representation, in which we start with an ensemble of initial conditions, an ensemble of forcing, or an ensemble of data observations or perturbed observations, and we run the model into the future, basically a forward run, in order to have an ensemble of solutions into the future. And then instead of analyzing a single solution trajectory, we analyze the statistical distribution of the solution. And this basically builds confidence in the solution, in which we now have uncertainty bounds on our prediction that guides us and basically gives us confidence in whether we need to trust the prediction or we need to be careful with the prediction that we have. And here, data assimilation or downscaling would be used to guide the solution to have a consistent solution at a solution trajectory. And first, we start with the first avenue of downscaling, which is dynamical downscaling, in which we're injecting data into the model, into a dynamical model, to constrain the prediction of the model with the core scale data that we're observing. And this is generally done by nudging the system of equations by adding a source term to the right-hand side of the equation that forces the solution towards the data. There are three main approaches to do so. First is grid nudging, in which we inject the data at grid points where we have the observations only. In this sense, you can think about a delta function that injects all of the energy from the observation to the solution that you get from the numerical model. And the problem with this approach is that it's not consistent. It doesn't have proper foundations. So it might work. In some cases, it might fail because the resolution will be too coarse of the data. Another approach is spectral nudging, in which we're nudging the low frequencies. Here we can think about the Fourier spectrum. We're nudging the low frequencies to the low frequencies of the data. But the problem here is that what is the resolution or what is the frequency for the cutoff? There are no specific guidelines, and people generally resort to heuristics where they try and see if the results would work. Finally, the newest approach would be continuous data assimilation, which is built on foundational theoretical guarantees, in which we're nudging the large scales of the solution to the large scales that we're observing. So now there's no question of cutoff or question of energy being injected as a delta function, in which we're spreading out the energy. The nice thing about CDA is that, or continuous data assimilation, is that it's based on a theoretical lifting function that lifts the core scale solution trajectory to its higher resolution counterpart. And it can do so dynamically through CDA by nudging the core scales to the core scales. And the high resolution solution that we get from the CDA algorithm approaches the reference solution, which we only have observations of exponentially fast in time, which is currently the fastest thing that you can get with the dynamical downscaling algorithm. And the idea here is that we're chaining the fine scales of the solution inside the grid points by the observations at the coarser grid. The way we do so is that basically we introduce to the right-hand side of the equation, so du by dt is equal to f of u is a general dissipative dynamical system. For this dissipative dynamical system, and I'm stressing on dissipative because you need the viscosity for this system, for this algorithm to work, we add the nudging term, which is the interpolated solution at the high resolution minus the interpolated solution at the from the observations with some nudging factor mu. And I think the second one is a typo. It's only one at the outside. Okay. Yeah. But basically, the idea is you're trying to compare the interpolated solution from the core scales and the interpolated solution from your fine scale solution, and you're trying to compare the large scales now, your larger patch.
What you say is how this the velocity field in the turbine.
Yeah. this brings us to the theorem from Aswani, Tolson, and DT from 2014, that basically your solution converges to the reference solution exponentially fast in time, or your error goes to zero exponentially fast in time, provided that your data is dense enough, so your observations are close enough, and your nudging is strong enough, mu is large enough, and these both depend on the viscosity. So you have guarantees on the viscosity, basically that relates the H, mu, and the viscosity in one formula. And this is nice because now you can basically get estimates of how strong you can nudge a priori. Now, the nice thing about it is that there's another theorem that regardless of the viscosity that you have, for some specific chaotic systems, such as the Rayleigh-Benard, which I'll be focusing on, you can go to infinite nudging, so your mu can go to infinity, but numerically this is not stable. But still, with a general dissipative system, our experiences have shown that you can go with larger nudging than what the theorem tells you, which is also a really nice takeaway. And now the thing is, up till this point, CDA has only been studied in the noise-free case, except for one theoretical study by Bissai, Olson, and Beatty, in which they say that if you have a solution of a system with some perturbations of the data that are perturbed with a Gaussian noise of standard deviation of variance sigma, then the error or the lim-sup, the maximum error at infinity of the squared error or the expected squared error of an ensemble of downscale solution is proportional to a constant that depends on the nudging, viscosity, the length scale of the observations, and the length scale of the problem itself, multiplied by the trace of the covariance. And here I stress on the C being as a constant with no actual dependence that's actually known theoretically. And this is what we're trying to quantify in some sense, and to validate that indeed numerically we can have the squared error or the mean squared error proportion to the trace of the covariance.
What's the variance?
This is the covariance.
Of the
Noise.
of the
Yeah.
normal.
Yes. For in this case, it's only normally distributed. This is what the theory tells us. And the problem with CDA is that since we're applying nudging at every single time step, so basically you keep on nudging with the previous data at every single model time step, it can become expensive, especially that you're using previous data from the last time you actually had acquired data into the next time step when you have new data. So it's a bit expensive, and it's hard to twist your mind around it to get high estimates or high accuracy estimates of the state. So we propose a discrete in-time variant of CDA in which we apply the nudging CDA equations only at the time steps when we have the data. And on other time steps, we resolve the full system. And the objective of this study would be to compare CDA and DDA in the uncertain settings. So now we have noise in the observations, and we compare their numerical performance. We compare our findings in terms of squared error to the theory. We compare the statistical distributions of both algorithms and so on.
Sorry, what's the other one?
Which one? Comparison to the theory or?
The second bullet.
Yeah. Yeah. So basically in DDA, what we propose a new algorithm based on the CDA equations. So these are the CDA equations in some sense. You have any dissipative system, you add with some nudging. Basically, what we're trying to say that with CDA, you're continuously nudging the system with previous data. So if you have data at this time step and your model time step is small delta t, you keep on nudging with the data at time t till your t plus TO where you have the next observation. In DDA, the one that we propose, you only nudge at the time when you have an observation, and then yes. And what we show, basically, you see that the result is really nice because now you have a way to relax your system by solving the actual system. Basically, you apply a nudging at delta and time, and then in time it resolves. And we focused on the Rayleigh-Benard convection system, which is a thermofluidic instability, in which you have a heated plate at the bottom, a cooled plate at the top, and then due to buoyancy effects, due to the temperature gradient, we have some circulation. And if you increase, and basically it has two dimensionless numbers that govern how turbulent the flow is, the Rayleigh number and the Prandtl number. Basically, here we fix the Prandtl number as air, 0.7, and then we change the Rayleigh number to have a highly turbulent flow. And here you can see the CDA solution, the reference solution, and the difference between the two. And you can see that the solution converges exponentially fast in time because we're applying the CDA nudging. And here you can see how the CDA nudging can be applied in an equation.
Here, how many observations do you have in this problem?
Next slide.
Oh,
Yeah.
sorry.
So here you can see that here I'm showing the ensemble, the RMSEs of an ensemble of 50 different realizations for a downscaling factor in space 5 and in time 10. So we have one observation every 10 time step and an observation coarse scale grid that is 5 times coarser in X and Y. So you have 25 times coarser in space and 10 times in time, which is significant. And then we compare the RRMSE curves of 50 different downscaled runs based on CDA and DDA. And we can see that the CDA members all collapse on top of each other. They all give similar RRMSEs, not only similar RRMSEs, but similar fields themselves. Whereas the DDA has a bit more spread. We also noticed that the DDA RRMSEs at the plateau are lower than those of CDA. And we also show that the exponential convergence. So you can see that CDA quickly drops, it reaches the plateau and continues at the plateau.
This is every 10 times step. So you
Yeah.
in the observation.
Yep.
You expect the DDA to perform better as this number increases, right?
Yes, because you're relaxing it a bit more. And this is exactly what we show in the later experiment. So this is the next step. Basically, now we look at the functional dependency where we compute the mean squared error of an ensemble of 50 downscaled realizations compared to the reference. And we look at the functional dependencies of how this mean squared error changes with the noise level. We can see that it is proportional to the variance of the noise, which is exactly the theorem that Bisaya, Wilson, and Titi had in 2015. Then we look at the change in the mean squared error with respect to the spatial resolution, and we can see that as the resolution gets coarser, the mean squared error increases, and the functional dependency is linear. So the coarser it is, the higher the error is, which is expected because you're trying to chain the fine scales with coarser observations. For time, we can see that the DDA solution has a mean squared error that is nonlinear, has the S shape, whereas the CDA solution has increasing errors with coarser temporal resolution at a linear rate. And this is nice because now you can expect that if you miss an observation, what is the error that you expect? If for some reason some measurement is missing, what is the error expected in that patch? It's nice estimates that you can get, and it also improves the knowledge on the literature. Oh, sure.
Trying to profit the last problem.
The last one, basically, the average mean squared error of 50 downscaled realizations for CDA and DDA. There is a certain threshold beyond which the DDA solution has an inflection point, and you can no longer assimilate because your system becomes highly nonlinear. So you're adding noise, and this noise will basically, remember the slide that we had on stochastic representations. You have very highly nonlinear models, you have bifurcations, your system is going to split into multi-model distributions, and then it's harder to assimilate them all into a single one. But there is a certain threshold beyond which the DDA doesn't work. Whereas CDA is consistent because we have the theory that tells you if you consistently keep on nudging the system with the previous observations, you're chaining the fine scale solutions. And this is the reason for that. And then we look at statistical distributions. Basically, we have 50 downscaled members from DDA and CDA. Again, I kept the same colors, orange for CDA and blue for DDA. We can see that the DDA solution has larger spread. You can see the spread in the RMSEs on the left y-axis, but a 3 times lower RMSE compared to CDA. We can also, we applied the Kolmogorov-Smirnov test to test for Gaussianity, and we can see that the downscaled members are indeed normally distributed. We also check if we average the 50 downscaled solutions, whether we can get a better estimate of the state compared to individual realizations, which we actually get. If you compare the left plot where you have individual realizations on a box plot with the average solution on the right, on the plot on the right, you can see lower errors by averaging the solution, which is also nice to have. So it means that if you have a lot of downscaled solutions, averaging them out will give you one solution with a better state estimate than individual realizations. And then we look at the problem that, what if our temperature observations are very noisy? We know that there's a specific feature of the Rayleigh-Benard system that the temperature and the momentum and temperature equations are coupled, such that if you remove temperature observations, the CDA solution will still work because the temperature observations will only rely on the nudging in the velocities because of the coupling. The other way doesn't work due to the buoyancy term. So what we do here is that we fix the velocity noise level. It's as if you have a velocity sensor that's fixed, you don't change it, but you have different options for temperature sensors, different options with different quality measurements. And here we notice that for a certain noise level of the temperature measurement device, then you can neglect or remove any temperature observations and rely only on velocity observations that are already noisy and be able to get a better state estimate than using both observations, which is nice because it tells you that the quality of the observation that you have is more important than the amount of data that you have. So the idea here in this project is that we proposed a new discrete and time variant of continuous data assimilation. We compared both algorithms and validating the theoretical guarantees that we have from Besai, Olson, and TT, Azwani, Olson, and TT. And we looked at different scenarios in which the statistical solution was analyzed to check for Gaussianity, to check for the solution accuracy, and so on. And also show that if temperature observations become very noisy, it's better to discard them in favor for the velocity observations alone. This moves us to the next project, which is on CDA, physics-informed deep neural network for downscaling dissipative flows. And the idea here is that CDA is a dynamical downscaling algorithm. So you're required to solve the system of equations at a high resolution mesh in order to approximate the state at the high resolution by injecting the core scale data. But the CDA comes from a bigger, stronger theory called the determining form map, which offers a theorem that tells you that there exists a unique lifting function that goes from the core scale solution trajectory to its high resolution counterpart. So basically now you just need to evaluate a single function to go from the low resolution to the high resolution trajectory. Time is part of it. Here we looked at deep learning in order to approximate this lifting function, since it doesn't have any closed form solution. It's generally intractable. You don't have an actual guideline of how to evaluate it. So we approximate it with deep learning. And the idea here is that we know that from statistical downscaling, builds a lifting function, which is deterministic from the core scale data to the higher resolution data, based on a historical data trajectory that links the core scales and the fine scales. And the idea here is that you're trying to push the distribution, the statistical distribution, from the low resolution to the high resolution, in order for it to represent more or less the high resolution solutions from the data set that you have. And this is based on any statistical method, such as regression, whether quantile regression or regular regression on the data.
There's a picture here.
Yes.
Are these correct?
Yes.
Because if you see
Yes.
a low resolution,
Yes.
you don't expect that the higher resolution.
This is why downscaling is important, because if you don't synchronize the two solutions, this is what you get. Your core scale model will diverge from the data, whereas your high resolution model is high fidelity. It will stay consistent with the data. This is why the project is really interesting.
But these are one-to-one.
Mhm. Basically, the only difference was the resolution of the model. The same thing. Yeah. So the determining form map is a unique. So basically, there's only one. You can get another one that gives you the same effect. It's isomorphic. You can go from low to high or from high resolution to low resolution. And it's Lipschitz continuous, meaning it's basically bound, the gradients are bounded. Everything is well behaved. It's a lifting function from the low resolution to the high resolution trajectories. And it works for infinite dimensional dissipative dynamical systems. And here the main takeaway is that it works with the 2D Navier-Stokes equations, because it has been theorized with a lot of theories that the solution of the 2D Navier-Stokes exists on an infinite dimensional manifold. This is Yanis Gavrikides, if I believe correctly. And basically, what Foesh, Joly, Kravchenko, and Titi proposed in 2012, 14, and 17 is that They started with the interpret operator and moved towards the nodal points, Fourier modes, and so on. But the idea here is that if you have a solution on the projected solution of high resolution trajectory, and you have many of these low resolution projections, then they all look similar, then they have to come from the same solution trajectory. And the idea to explain this to a 5-year-old is to imagine you have an army of M people with different levels of eye vision. So they have bad vision, and they all look at the same solution trajectory, and they all agree that these are the same, then most probably they're coming from the same trajectory at the higher resolution. And now we look at deep learning, which is a class of AI in which we're trying to represent a mathematical function through stacking many nonlinear functions in order to understand data better. And what we mean by understanding data is that we're trying to understand data from different structures, different types, in which whether it's a Markov decision process, such as driving a car, or generating 3D images, forecasting complex models such as the environment, or even simpler problems such as identifying objects in real life. And what we came up with is the CDA-Net architecture, in which it's composed of a two-stage neural network, starting with a 3D convolutional neural network for feature extraction. So you give it a low resolution trajectory in space and time. Again, we have to stick to the theorem in the sense that our input is a solution trajectory at a coarse spatiotemporal resolution. First, let's input a 3D unit. It extracts the spatiotemporal features, since it's 3D, 2D for space and 1D in time, with different convolutional kernel sizes for space and time. The output of the 3D unit would be a 3D spatiotemporal features grid. So for each point, we now have a features vector that basically summarizing all of the features that we've seen from this input clip, low resolution input clip. Now, each of the features vector is then put into an MLP in an implicit neural network representation, where we concatenate the features vector with its corresponding coordinates, the spatiotemporal coordinates, so X, Y, and time. And what this will give us is that we can propagate it through another stack of nonlinear functions to predict the solution of the PDE. This is nice because now we can apply backward passes in the neural network to estimate the gradients or the derivative of the output with respect to the input. So we can have the derivative of the temperature, pressure, and the velocities with respect to the coordinates X, Y, and T. What's even better in this architecture is that since we're using a switch activation function, which is analytic, then we can get any higher order derivative that we want. What's even nicer is that once this is trained, then the MLP can be used at any spatiotemporal coordinate, meaning you have infinite resolution. You can apply it at the same resolution where you trained it on, or you can let the neural network interpolate between the points where you have the training data. And this is very powerful because you can go to infinite resolution. And with it, it's nice. And this is a schematic of the pipeline in which the input at the coarse resolution clip is input to the model. It first gets propagated through the 3D unit. Then the latent grid is output from the unit. We use the features vector with the coordinates to predict the temperature, pressure, and the velocities, which are the solution of the PDE. And then during training, we have two loss terms to form the total loss function. The first loss term is basically from the data, which is the regression loss, simple L2 or L1 loss, up to you. And then we have a loss on the PDE, in which we evaluate our prediction using the backward propagation of the neural network, evaluate the norm of the residual of the PDE. So we move everything to the left-hand side, and we evaluate the norm of the left-hand side of the PDE, basically the error committed by the prediction of the PDE. And we have a weighted sum of the two norms to train our neural network. And first, let's see how CDA-Net perform.
How do you acquire or synthesize the ensemble of force trajectories?
Basically, for now, we resort to the theorem itself. For now, it's just the theoretical aspect. There are two. What we did now is that we run the high resolution model and we coarsen it by subsampling, as if you have measurement devices at every S steps. But there's another work that we try to do. This is the first chapter. Basically, you can run the low resolution model. This would This will give you the data, and then you can downscale the low resolution model to give you high resolution data, and then you do the both. This is what you'll see in the next chapter as well. So this is the solution for CDA-NET when we downscale a flow field at real number of 1 million with spatial and temporal coarsening of 4 times in space and time. So you have 16 in space, 4, and 4 in time. And you can see that comparing it to CDA, both CDA and CDA-NET are quite fast to get to the plateau. So you get quite fast to the 0 error in some sense. CDA-NET, of course, will have a higher error compared to CDA, since CDA-NET is an approximation of the lifting function. It's not a deterministic approach, whereas CDA is deterministic. You're actually going to the equations, and you're solving the high-resolution equations themselves. But again, it's at a fraction of the cost. And then we run the errors for different cases. Here I'm only showing 3 cases for S and T, 2 and 2. So basically 2 times coarsening in each direction in space and 2 in time. So 8 times reduction. We can see that the errors are below 1%. The same thing for 4 and 4. We can see that the error is around 1% for CDA-NET, whereas CDA can go to 0 error, which is the theorem. And for 8 and 8, we can see that the errors are indeed higher because the problem is much more complex, but still the errors are below 10%, which are reasonable for this type of application. And then we test for generalizability in the sense that we don't want to train the neural network for every single real number or every single flow. Can we see if this lifting function that we approximated can work for different flows that are similar in some sense, or the structures are similar? So here we trained it for the real number of 10 to the power 6, shown in black with the dot. And we tested it on trajectories that are not seen for different real numbers, lower and higher. So less complex or much more complex with more fine scale features. And you can see that the error is more or less preserved. So you can basically use the same neural network that's trained for one real number for flows that are somewhat similar. Finally, since we've seen from the last work that for the real linear convection system, we can basically downscale the system without temperature observations, we try to see if CDA-NET can also have the same features. And indeed, we saw something interesting in the sense that with velocity observations only, we're able to converge with CDA with 0 error. So this is the RMC of the temperature and the velocity. We can see that when we don't have temperature observations, the error in the temperature is higher for both CDA and CDA-NET. But the nice thing is that CDA doesn't convert, it blows up at the end. Whereas in the velocity observations, we can see that CDA and CDA-NET can have better errors when you observe the temperature, but when you observe only the temperature, then it blows up, which is consistent with the theorem. And here in the conclusion for this one is that we propose a new physics-informed deep neural network that approximates the effect of the lifting function. And now we can do downscaling fast, much faster than CDA, in which we evaluate a function on a coarse resolution trajectory to give us the higher resolution trajectory. And we have a way of having infinite resolution in space and time by evaluating the function many times in between the observations, which is basically chaining the coarse scale observation, the fine scales to the coarse scales. And now we have an efficient tool for downscaling distributed flows. So now we can start thinking about the uncertain setting in which we have large ensembles. And this is the next work in which we apply downscaling for in the case when we have observational and model errors. And here basically we look at the lifting function or the CDA-NET as a function f theta that goes from the coarse scale solution trajectory to the high resolution trajectory. But here we only studied it in the perfect setting in which we have perfect training conditions, no noise, our data is perfect, we have control over everything. But what if in the real setting where we don't have any control? So we try to look at the case where our validation data set has errors in the data or in the model. So basically, imagine you have model errors in the Navier-Stokes system when you're solving it. How would this have an effect on the outputs? So basically, we inject this error into the neural network parameters by perturbing the parameters themselves. And we have perturbations into the input by sampling white noise and adding it to the data itself. And here we look at 3 training scenarios. The first one is the perfect training scenario in which there's no noise in the input, no noise in the model, and we train the model perfectly. And here the idea is to compare the performance of CDA-NET with the theoretical guarantees that we had from Messiah. And in the first scenario, if we increase the model noise, we can see that the top row, we can see that the errors are increasing. However, they don't have any specific pattern or structure. So basically, it's the imprint from the convolutional kernels on the output prediction. Everything. Basically, we choose, so the model noise here is a fraction of the variance of the activations. So basically, if the standard deviation of the activations is 1, we choose 2.5 or 2.5% or 0.1% or whatever. So basically, you have a control that you're not perturbing with a single noise level everywhere, because you don't know the value of the activations or the value of the weights of biases in the neural network. But you have an estimate of the variance or the mean, or which is more relative. The errors are relative to the variance in the parameters. Another approach would be to perturb the outputs at every single layer, but this was shown in another paper in James that it doesn't give you reliable results.
Basically, in the model, you take the root, which is the solution of the governing equation, and then you perturb the result.
No, the perturbation is in the set class of the CDA net. So you have a lifting function.
No, I'm talking about the physical model. How does the physical
I didn't perturb the physical model. I have data, low resolution, high resolution, and then I perturb the model itself. And by perturbing the lifting function, it's as if you're perturbing the mapping between the two manifolds, and this is similar to perturbing the solution of the Navier-Stokes equation. It's as if you don't have the actual equation or the CDA system. You're perturbing a slightly different system. Okay. And basically, when we add model noise, we're basically seeing the imprint of the convolutional kernels on the outputs, whereas adding observational noise emphasizes the physical structure or patterns, where you have formation of plumes, mixing, or basically turbulent structures are better seen with a higher error. Then we do the same thing with the functional representations, and we notice that the mean squared error is proportional to the variance of the noise level, whether observational or model noise, which was really nice to see, because it's also consistent with the theory that we have from Besayhausen and Titi. However, now we can see a small plateau at low errors. This is where the errors from a surrogate model are higher than the errors that are injected to the data or the model. And basically, this is what we call representation errors, that our approximate model can't do the same performance as a real dynamical model. We do the same thing with Rayleigh numbers, with the Rayleigh number on the left, and you can see that the effect is not significant at all, which is expected since the lifting function is unique isomorphic, provided that the conditions are met. And here we made sure that our data satisfies the conditions, so our errors are similar. For the spatial resolution, we didn't see any effect, which is also part of the theory that Foish et al. Had. Finally, for the temporal resolution, we noticed that the CDA net has a very strong sensitivity to temporal resolution, which was not as expected. We had a quadratic dependency, which is very high. Then we looked at the second training scenario in which we perturbed the data and the model during training. Basically, now we have model errors and observational errors during training, and we check its effect on when we have noisy data in the validation, or when you actually apply your system. And here we again see the similar performance with higher representational errors. So basically now we have your representation of a model will become a bit worse, which is expected since your data is worse and your estimate of the model is worse. But it behaves similarly for higher noise levels, which is also nice to see, which means that the structure of the CDA net is actually a representation or a close representation of this lifting function. When you look at the tables showing the mean RMSE of 50 realizations and the standard deviation of the downscaled fields, the RMSEs, we can see that adding observational noise level along the vertical, we can see that the errors are higher, your mean errors are higher, but basically increase faster than increasing model errors. But increasing model errors along the x-axis increases the spread in the members. And this is similar to what we've seen in the first project, in which adding observational noise leads the CDA members to collapse on top of each other. Here we see something similar, that adding observational noise error with almost zero model errors doesn't contribute much to the standard deviation. And for the final setting, this is where we go back to perfect model errors. We start with course resolution data. We run our CDA algorithm to get the high resolution data set. And we run CDA with the wrong or the incorrect viscosity. So now we have even more model errors in getting the high resolution data. Then we coarsen the data to generate our input data set and train our FTATA or the CDA net to get the high resolution data. And here, basically, we also see that whether you're evaluating on the true data set or the incorrect viscosity data set, we're able to have similar performance. So the model generalizes. You have higher representation errors compared to the previous two cases, but the same functional dependence. Now, all of this is nice. Everything is cool. But the main takeaway of the entire thing is that why not have all of the control while training the data set, while training the neural network? You have control. You use perfect data, train the model, and then you expect higher representation errors during deployment. So you deploy your model, you expect higher errors in the model in the observations, but what we showed here is that whether you use perfect data sets for training, imperfect data sets for training, or even downscale products for training, you're able to have similar performance. But if you're training with the best that you have the best representation of the CDNet model, and then you can use that for downscaling into the future, which is very powerful because now you can generate your own data set that you have control over, and then you apply it in the real life. And the main take-home messages is that basically we compared the performance of CDA and DDA. So we established our baseline on how the state-of-the-art downscaling algorithms work, how they perform in the presence of noise. Then we propose a new algorithm called DDA, which is based on the CDA, but however, it doesn't have any theoretical guarantees for the moment. Based on that, we propose a new CDA net neural network that is physics informed and much faster than CDA since it's a statistical downscaling algorithm and consistent with the PDEs to the best that it can based on the optimality criteria. That was also shown to be able to downscale a large number of ensemble members much faster than downscaling dynamically. And just for sake of interest, I also showed some side projects for anyone interested in future collaborations or any discussion. So a similar approach with physics-informed deep neural network was used for backward in time predictions. Basically, backward in time predictions is as an ILPOS problem. You can't go backward in time, especially if you have viscosity. And generally what people rely on is an adjoint or tangent linear model. And these are linearized models, so they're first order accurate. Whereas with neural networks, you can go with higher order nonlinear schemes, and you can go backward in time much more consistently. And this is what we showed in this work. We also worked on deep reinforcement learning for data assimilation. This would be maybe in the future for a future talk, where it's also based on state estimation, but based on nonlinear optimal control approaches. And this is where most of my first research project was on moving source pollution identification in the Mediterranean. Then we worked on neural networks for semantic segmentations of mesoscale eddies, which transport heat and salt. Basically, you need to understand where they lie to have proper estimates of the budget. We also worked on surrogate models for uncertainty quantification to estimate the sensitivity of oil spill models, whether it's evaporation processes, dispersion, emulsification, with respect to different parameters of the oil parameters or the model parameters. And I think this is the last one where we use remote sensing data to estimate the chlorophyll concentration at the surface using a Bayesian neural network instead of deterministic methods, because you're using very coarse data that's thousands of kilometers away from Earth to give you one prediction of the actual value of the chlorophyll at the surface, whereas a much more relaxing approach would be to actually have a distribution of the chlorophyll concentration and have confidence in your prediction. And with this, thank you.
Yeah, but that was awesome. A lot of things also see the last parts. I'm looking forward to what comes out of these. Maybe before I ask questions, any questions from the audience?
Thank you, Abid. I just had a question about the CDA when introduced the loss function. You said that there are two loss functions, one coming from regression. You said you introduced weights. Can you just say something about how you weigh them and how does this affect RMS errors?
So basically, the idea is that you have two loss terms. You have L total would be the sum of L regression plus some W multiplied by LPD. This W should be positive, of course, and it tells you how significant the PDE loss is relative to the regression loss. And this is a hyperparameter that you need to try. Basically, you try it on a log scale, 0.001, 0.01, 0.11, and you check the results that you get. Once you get once you get into the ballpark, then you can fine tune a bit more if you want to do that.
Got it. So how is this related? Looks similar to the physics-informed neural network.
It is, but
So the CDA part, where does CDA come in?
So the difference between physics-informed neural networks and what we propose is that physics-informed neural networks, you're casting your PDEs into their variation form, and you're trying to minimize the cost function, the PDEs as a cost function. So you're trying to solve the variational form of the PDEs.
Yeah.
But the variational form is the weak form of the solution. It gives you the weak form of the solution. One. Two, not all solutions admit a variational solution. So this is why there's another paper by Oxford and Philip Taj's group, provably accurate physics-informed neural networks, where they show that the errors are order one with pins.
Mhm.
The difference here is that our regression loss is basically you're fitting the data similar to statistical downscaling, but you're adding the LPDE, the PDE loss, as a weak constraint on the prediction. So now your predictions are constrained with a weak constraint with basically the PDEs. So you want to satisfy the PDEs, but you're not putting it as a hard constraint.
Mhm.
You
Yeah.
see? The difference with physics informed, you have a hard constraint with the PDEs, PDE loss. This is what you're trying to minimize. And then you have a weak constraint on the data or the boundary condition.
Isn't that dependent on the hyperparameters, right? And also in pins, you have some hyperparameter that
Yeah.
decides how much weight you want to give to the PDE, right?
Yes, but again, the way you constrain your predictions is different. You see that this is the main difference.
Nice. Okay. Nice. Yes.
No, just to carry on this, so the term in the loss function where you satisfy the PD, it's pointwise satisfying the
Yes.
PD.
But
And at which resolution?
Monte Carlo, random selection.
Ah,
Yes.
okay.
You presented the work and results that apparently are valid only for the 2D Navier-Stokes.
The nice thing about this is a very good question, actually. Because we don't have any existence or uniqueness on the 3D Navier-Stokes, we can't say anything. However, there are other work that do it for the 3D Navier-Stokes.
And it shows promise.
Yeah, and numerically it works. But here, since we're trying to extend the theory, we are stuck to the 2D. But yeah, it works.
So the theorems of TT and Co, they're only applicable at least as a theory to the 2D Navier-Stokes.
Now, what Idris says in every single conference he goes to is that he has a list of paper, a big chunk of papers for the 3D case, that once someone pushes forward the 3D existence and uniqueness, he can publish a number of papers. So he can
Once
have
he's
a new
waiting
case.
for that,
Yeah.
that's amazing. Who knows, maybe.
Thank you for the nice talk. Can you please take the system of ODE I put before? Yes.
PDEs.
ODE system.
Everything is a PDE.
The ODE.
I didn't do anything with ODEs. Everything is a PDE. Yeah, it's still everything is a PDE.
This one here.
Yeah.
So how do you generate the function capital F?
No.
How do you get it?
No. du by dt is equal to f of u is your dissipative dynamical system.
I'm not hearing, sorry.
Du by dt
Yeah.
is equal to f of u. The one in black is your original system.
Okay, so
Yes.
it's not related to Navier-Stokes or anything.
It is. It could be Navier-Stokes. It could be Rayleigh-Benard. So here,
Yeah.
you see this equation is the same thing as the one I presented at the beginning. No. This is continuous for no. So du by dt. Yes, exactly. So the right hand side of the equation, you have it's as if you're moving your terms. D theta by dt is equal to f of here f of theta would be 1 over square root of number Laplacian of theta. It has to be distributed.
So you
have
put
to
this,
Laplacian.
you put then the system in that form,
Yes.
basically.
Yes.
Okay. Now, I come to the second question. Have you thought about using neural ODEs for,
Not yet. No.
not yet?
No.
Mm.
Because again, this is dynamical downscaling. Dynamical downscaling is very expensive. So even if you have a surrogate for the function, you still have to solve the solution.
Okay.
If your model is not as reliable, so here you're relying on you're using a high fidelity model to have high fidelity estimates of the state. So if you have a lower fidelity model, you shouldn't expect better accuracy in the downscale product.
Okay. Thank you.
Thank you.
Great. Any other questions? Maybe I'll ask a question. At some point when you were comparing CDA with CDA net, you had these fluctuations in the
Yes.
errors. Is
Yes.
that due to the number of time steps you need to apply the nudging? Because you're applying the nudging after a certain number of time steps.
Yeah, so basically you nudge,
Yeah.
your errors will rise because every single
Yeah.
time that you keep on nudging. What was nice is that the CDA net model was able to pick up these fluctuations as well. So its interpolation in time is not as good as we expected, which is a nice takeaway. Because you see, CDA fluctuates, but it fluctuates because you nudge, then you keep on nudging with the previous solution, but the errors will increase. They are bounded, but they increase. You nudge the next time, it increases. Nudge. For CDA net, it was interesting to see because there's no nudging, you're only lifting. But
I see.
still, the errors fluctuate because the interpolation in time, you shouldn't expect it to be perfect. The same thing is what we saw with the backward time prediction. If you're trying to interpolate in between steps, you have jumps. Yeah.
And so how do you decide the number of time steps you need for nudging? Because that depends on how much data you have, right?
This is the data. This is why we said that. This is why I said that the difference between here, what we have with CDA and spectral nudging, is spectral nudging. You have to have heuristics on where to have the cutoff in the frequencies domain. Here we don't have any tweaking around except for the nudging factor. And what the theorem tells you is that if you have weak nudging, you're going to go exponentially fast in time with e to the power minus mu something.
Yeah.
But if you have higher nudging, then e to the power minus mu something would be very large. So you drop the error much faster.
So you have constraint on how many time steps you need to
No,
do the nudging.
the time steps are basically dependent on the data that you have and the resolution of your high resolution solution. So
Okay,
this is a model parameter basically.
cool. Right.
Since your talk was about downscaling, can you tell us what's the state of the art of methods in downscaling that are used in weather forecasts,
CDA.
WRF and so on?
CDA. This is what
The CDA.
Srinivas has two papers. Srinivas with Rahim and Omar, and at least they have two papers applying CDA in the case of an application to war. I'm also working with Peng on the.
But currently, for example, if I download WRF, the latest WRF, and do downscaling, CDA isn't there or what?
No, they have spectral nudging.
Spectral nudging. So basically what you're presenting is not one level above, two levels above. So spectral nudging, the next best thing is CDA, and probably the next, depending on.
There is a CDA++ where you have double exponential nudging, but it's still early on.
And
Still
you
a
think
big-
that DDA would even give you better results in that case, or not necessarily than the CDA?
We need to try. We don't know. Because
Okay.
now our tests are only on the 2D Navier-Stokes, and it showed better results, but for the 3D things might change.
Okay.
But I know with Peng, we're using the 3D DDA because CDA is almost impossible with high resolution model. With the state, when your state gets to 10 to the power 10, DDA is the only choice.
Very nice. Cool.
All right, thank you. Thank you, Abid. Thank you all for coming. If you have more questions, maybe we can take those offline. And yeah, thanks for being here. Thank you.